All right, this is Chemistry CP on Friday, October 30th, 2020. The new material is mixing two substances together at two different initial temperatures. Yikes. Mixing two substances together that are initially at two different initial temperatures. And I need to activate my earbuds so I can hear you students without recording the sound of your voices. Here we go. I have a container of water. Samantha, how much water do I have in my container? Well, sure. All right. I have a volume of 32 milliliters of water. Of course, I need to convert that to mass. And as I've often tried to teach you, density is mass divided by volume. So the mass of this water will be equal to the density of the water times the volume of the water. Esther, what is the density of water? From memory. Esther, repeat please. Oh, the question is, what is the density of water? All right, child, hold that thought. The timer just went off. You have a 3-minute break. I'll come back and torture you in 3 minutes. Da 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 da. All right, children, 3 minutes of your life have gone by. You are 3 minutes older now, wiser, mature, and able to answer any question I put to you. Esther G, no doubt you spent the past 3 minutes scouring over your notes. What is the density of water? No units? That hurts. 1 gram per milliliter. So we're going to take the volume of 32 milliliters and multiply it by 1 gram per milliliter. Even I can do that one in my head without a calculator. I get 32 grams. Seems like a silly step, but it is necessary that you prove to me that you understand the difference between volume and mass. In the case of water, we've set the density to 1 gram per milliliter, which is great. For anything else, oh man, you better use the right value. But wait, there's this water is at some unknown initial temperature. Oh, Mindy, in Celsius, it's kind of cool. What is the temperature of this water? You call that cool? That's hotter than your human body. 40 degrees Celsius is the initial temperature of this water. Wow. Okay. So we have 32 grams and it's at 40 degrees Celsius. And now I'm going to add some more water. How much water am I adding, Giselle? Oh, you guys are not doing a lot of water. Okay, so this water is 20 milliliters. I remind you that the density of water is 1 gram per milliliter. So I'm going to list this as 20 grams of water, which, by the way, these are very small quantities of water. So mathematically, we can do them, but in real life, I would hope you would use 200 milliliters instead of 20 and 320 instead of 32 if we actually did this experiment in school. But wait, this water is at a significantly different temperature than 40 degrees. Eric Lee, what is the temperature of this water? Repeat that, please. Did you say 42 degrees Celsius? I said significantly different. You're fired from 40 degrees. Alyssa, significantly different, but it still needs to be liquid water. So somewhere between 0 and 100, but don't have it very close to 40. Um, my goodness. 86 degrees Celsius. There we go. I can work with that. All right. So I'm taking this hot water and I'm mixing it with this cold water. And here is the mathematical concept. The heat lost by the hot stuff cooling down is set equal to the heat gained by the cold stuff warming up. All of this is presumed to take place inside a calorimeter where the lid is put on and no heat is allowed to go in, no heat is allowed to come out. And for a short period of time, that'll work okay, no doubt. So the only heat transfer is strictly inside the calorimeter between the hot stuff and the cold stuff. There's one thing that's common sense that you should use as a check. The final temperature, T sub F, is always, man, I'm using that word a lot these days, always between the coldest and hottest initial temperatures. This should be common sense, but it can serve as a check on your calculator result. So if we start off with the coldest temperature is 40 degrees Celsius and the hottest temperature is 86 degrees Celsius, then after we mix them together, our final temperature should not be any colder than 40 degrees and it should not be any hotter than 86 degrees. There's only one special case where the temperature would always be halfway between the two. And that special case is only if it's the same substance in both cases and it's equal masses of the substances. Imagine if I put a small hot drop of water into a big bucket of cold water. The final temperature is not going to be halfway between them. It will barely move at all. So don't just say, oh, give me the average temperature and I'm done. No, no, no. That's not enough fun. To find the final temperature. So that's what we're going to do right now. Find the final temperature. we are going to, interesting, calculate for the unknown final temperature. The unknown final temperature. Mathematically, I'm going to do, Q equals mc delta T, and I'm going to apply it to both the hot water and to the cold water. I'll put one side on one side of the equal sign. I'll put the other stuff on the other side of the equal sign. Doesn't matter to me which one you do first, hot or cold. I'll just do hot one first. Okay? So for the hot stuff, the mass is 20 grams. The specific heat of liquid water is 4.187 joules per gram per degree C. So we're using a double-paged reference sheet from the internet. For the temperature, I don't know the value of delta T. But what I do know is that 86 degrees Celsius minus the unknown final temperature is the change in temperature for the hot stuff cooling down. Okay, so that's pretty important. MQ delta T, filling in what we know. 20 grams, 4.187 joules per gram per degree Celsius. And for delta T, I'm writing it as the hot temperature, which we know, minus the unknown final temperature. Bless you, Giselle. That's for the hot stuff. Now, for the cold stuff that warms up, I foolishly reverse the minus sign. Esther, you found that humorous. Way to go, Esther. Really, the hot stuff should have a minus sign because it's how much you lost, and the cold stuff should have a plus sign because it's how much you gained. But I'm going to reverse the delta T order so that both sides have a positive quantity. So for the hot stuff, really, this should have been T final minus 86 degrees. Then you should put a minus sign out in front of it. Crazy. For the cold stuff, it's going to be the mass of the cold water, which was 32 grams, times the specific heat of liquid water, which is 4.187 joules per gram per degree Celsius, times, open parentheses, the final temperature of the water minus 40 degrees Celsius. So I'm writing this delta T in the reverse order that I had done on the left side, so that both left and right are positive quantities. Great. This is a Math 1 problem where I have one unknown, the final temperature of these two substances after they have mixed together. Mathematically, there's only one unknown here. We can solve for it. Amber, what's my next step? No one cares about the answer, child. I care what is the next step to get us all to the answer. Okay, we'll just chalk you up to being clueless for helping us educationally. Thank you for that contribution. I can't help but notice that because it's the same substance on both sides and it's in the same state, both in the liquid state, I can cancel the specific heat. You are allowed to do that, but again, it has to be same substance, same state. In this case, liquid water, specific heat cancels. All right, now just to write it mathematically so it looks a little bit easier, in fact, I'm going to write it without the units so you can see the naked math. Right now it looks like 20, open parentheses, 86 minus T final, close parentheses, equals 32, open parentheses, T final minus 40. I'm leaving off the units so that you can just see the naked math numbers and ponder to yourself, how am I going to solve for the final temperature? Emmanuel Savalos, any suggestions? I would use the distributive property. And Eric, get your camera back on. Distributive property. So that makes this thing 20 times 86 minus 20 times the final temperature equals 32 times the final temperature minus 32 times 40. This is where you would start to break out your calculator and ask, what's 20 times 86? And your calculator says, oh, clearly that's 1,720. And ask, what is 32 times 40? And your calculator says, oh, that's 1,280. Alexandro, now what? I would rather go the other way. Instead of subtracting 32 from both sides, Book of Life? You could. You might want to work on your background distractions there. All right, go mute yourself, child. So on the left, we have 1720. Now that I'm adding 20 times the final temperature to both sides, on the right, that makes it become 52 final temperature minus 1280. Vanity? Now what? Now I can. Aw, child, I'm going to have to just delete you from my conscious memory or move on to Saeed. Saeed, now what? Um, Are you asking me or are you telling me? Oh, okay, I'll do that. So when I add 1280 to both sides, the right side is 52 times the final temperature, and the left side becomes 3000 exactly. Woo! How's that for a round number? Okay, Mindy, what's the last step? Why do you students always say it so strangely? The way I would phrase it would be to say, divide both sides by 52. Divide both sides by 52. And for that, use your calculator. Beep, 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 and the calculator displays 57.7 degrees Celsius. But wait, does that make sense? Is that hotter than the coldest initial temperature and cooler than the hottest initial temperature? Why, yes, it's between these two temperatures. And really, it should be a little bit closer to the bottom one because there's more mass of the colder one. So this is a reasonably correct answer to this first problem that we've done today. I have 12 minutes and I'm going to do the second problem, and I really want to finish it in 12 minutes. Ready or not? Here we go. This would have been a lab activity that you would have done as part of this unit. The activity is to take a cube of copper. These copper cubes that we were going to give you have a mass of 20.0 grams. And what you would have done in the lab is put this on a hot plate and heat it up, crank it on high for 15 minutes or so to make it really, really hot. Then, using tongs, you would carefully lower it into a calorimeter that has some water in it and measure the change in temperature of the water. Okay, so typical numbers would be to have a mass. I'm going to skip doing it as volume because, density of water is 1 gram per milliliter. A mass of 150 grams of water with an initial temperature like 18.6 degrees Celsius. After the hot brass is dropped into this water, the final temperature might go up to something like 23, shall we say 23.1 degrees Celsius. And the question that we would ask you is, great, what was the initial temperature of the brass cube when it was on the hot plate before you added it to the cold water? The philosophy is the heat lost by the hot stuff cooling down is set equal to the heat gained by the cold stuff warming up. In this problem, we're dealing with water and copper, two different substances, two different specific heats. I'm going to blast through this. Here we go. For the copper, we can't calculate delta T because we don't know Q. And we certainly don't know the final temperature, or initial temperature, I mean. That's what we're supposed to figure out. What we can calculate is how much heat the cold water gained. So that's what we're going to calculate. The heat gained by the cold water warming up. Q equals mc delta T. In this situation, M is 150 grams. C is the specific heat of liquid water. You may have memorized it by now. I'm going to use a value of 4.187 joules per gram per degree Celsius. And for the change in temperature, I'm going to write it in reverse order. Actually, no, I'm writing it in the correct order. It's 23.1 degrees Celsius minus 18.6 degrees Celsius. And I'm getting too old to do that in my head. So my calculator says the delta T is 4.5 degrees Celsius. Okay. What do you get? Skyly, can I call on you? Do you have a value? Jessica, do you agree with that? Well, okay, I understand you're rounding off to 2 sig figs. I'm going to leave it to 3 sig figs and agree with both of you and say it's 2,800, I'll call it 30 joules. I'm going to leave it at 3 sig figs to the end of the problem. And technically speaking, we should be doing it to 3 sig figs. Okay, now here's the clever idea. This is the heat gained by the cold water warming up. It came from the hot copper cooling down. So this is the heat gained. I'm sorry, the heat lost by the hot copper cooling down. The heat gained is, well, technically the negative of the heat lost. But okay, this is how much heat was transferred from hot to cold. Now we can go figure out the delta T for the copper. Again, we're using the equation Q equals mc delta T, but now we're going to be using the data for the hot stuff, not for the cold stuff. In this case, the mass, well, let's see. We're going to rearrange the equation to solve for delta T. Delta T is equal to Q divided by M divided by C. The numbers that we're going to plug in are 2,830 joules. We divide that by the mass of the copper, which is 20.0 grams, and we divide that by the specific heat of copper. Go into this handy-dandy reference sheet, we find that copper only lists the specific heat in a solid form, which is great. It is 385 joules per kilogram per Kelvin, and we say, grumble, grumble, I want it in joules per gram, so I divide by 1,000, and I'm going to use a value of 0.385 joules per gram per degree Celsius. What do you get? Emmanuel M., can you come up with an answer? Yes. Hannah, do you agree with that? And hence, I have job security. Okay, I did not get anything close to that. I hear you losing points. Emmanuel Zavalos, go ahead and back me up and give the correct answer. Depends on when you round off, but okay. I got 368 degrees Celsius because I plugged in these numbers right here. Into my calculator, I typed 2830, divide by 20, divide by 0.385, enter. If you were to do that, you would get this. We're not done. We're not trying to calculate delta T. We're trying to find the initial temperature you see. This is the change in temperature, and I'm asking you what was the initial temperature of that copper cube when it was on the hot plate. Here's how we get it. Change in temperature is properly defined as the final temperature minus the initial temperature. In this particular problem, because I scrambled things with a minus sign, you should agree with me that the copper actually cooled down by 368 degrees. So really, the delta T is minus 368 degrees C. Now, to solve for the initial temperature, I'm going to just try to use common sense that says, well, if my final temperature is 23.1 degrees C and my initial temperature was 368 degrees higher, then I should add these two numbers together. And the result is the initial temperature was 391 degrees Celsius. It is my intention to create homework 7 to practice this last math skill for this unit. I'm going to make it due Sunday at midnight. When we meet next week, we're moving on to begin the next unit.